there's a good chance we should get through this part. We'll see. But I mean, all stuff is made of this stuff. All stuff is made of atoms of these different types of elements. So it's an important sort of class and all that. So an atom is the smallest unit of a substance that will retain its identity, okay? The chemical properties of that element. Element, remember we said that a substance can either be a mixture or a pure substance. And as a pure substance, it's either an element, which we're talking about, or a compound, where two or more elements are joined together with chemical bonds. The thing about an element is you have, no matter whatever magic wand you have, a destructive magic wand, you can whack on a bunch of atoms like copper atoms or carbon atoms, and you can't break them further with an ordinary wand. Now, my ordinary destructive wand would be one that breaks chemical bonds. You can get the power of nuclear destruction, and then you go ahead and crash down on an atom and actually can split an atom. So that would be extraordinary means. So here we have copper. We're going to kind of look at copper even more closely. This is looking at copper more closely. And this, I believe, is showing you, it's not your regular photography, not your regular microscope, but this would be the scanning electron microscope to show you kind of the contour, little bulges of the copper atoms that are joined together. That's pretty sweet. If I were to animate this, what it would do is we have, I don't know if you guys can see the red and the green in there. That's the center of an atom called the nucleus. And in the nucleus, the reason there is red and green in there is because within the nucleus we have positively charged protons and neutrally charged neutrons. So we have protons and neutrons in there. That thing I would animate goes zzz. Those are the electrons that are buzzing outside the nucleus. So those are three particles of an atom we call subatomic particles that you need to get a handle on. So elements on the periodic table. I actually brought a periodic table like the one I will give you on your test. So we don't have a test this week. The tests are always on Thursdays, but I think we have a test the next Thursday. Okay. So this is a periodic table like the one I will give you on your test. So, and this is the same one like is on the cover, but some elements have the symbol for the element is just a letter. Some elements have one letters like hydrogen. Some elements have two letters like iron is Fe. And it is case sensitive. So if there's two letters like iron, then the F is capitalized and the E is the lowercase. For whatever reason, I think it's because we say Na not applicable. Some semesters I've had students that for whatever reason they just really want to go. They want to go like this, and that's not it. Okay. Now that I've shown you, you're probably, oh man, that makes so sense. But sodium, of course, is capital N lowercase a. So it is case sensitive. On the next slide, I actually tell you there are a handful of elements. I say handful, there's more than 10 elements that you need to recognize the name and the symbol. And hopefully they're ones that you kind of already know. Sometimes students will be like, Mrs. Snipes, why is silver Ag? You're like, silver, that doesn't even, Ag, that's no Si in there. Well, here you can see that silver actually came from, I think that's Latin, argentum, okay? So that's kind of where they came from. So the reason I gave you this, or thought to give you this today, is if you wanted to, this could be something you could mark up. We're going to talk about periodic tables and how you know when information's on a periodic table. But you see already for each element, you have the symbol for the box, and then you also have a whole number. That whole number is called the atomic number. So this slide says, by atomic numbers, you should be able to recognize, if I give you the name, for instance, 1 through 20. So let's see, 1 through 20. That's hydrogen through calcium. If I give you Mg, what element is that? Magnesium, exactly. So all those 1 through 20 are fair game, and then we skip some 24 through 30, 35, 36, 46 through 48. So my point is, if you wanted to, you could take this and mark it up by atomic number, which you need to memorize the symbol which is given, but the name won't be given. Sometimes students are like, so I don't get a periodic table on the test? No, that's not what I said. You'll get a periodic table like this, but notice this does not have the names of the elements. Okay, and I say it's a little game, but honestly, it's probably in every general chemistry class, they're going to expect you to know something like that. All right, so there are 7 elements that like to always be buddied up with another atom. Now, that's actually specific to, that buddying up is specific to normal conditions on the Earth. And the conditions usually for will they buddy up or won't they would be temperature and pressure. Okay, so here they are. Those are the 7 elements. Like for instance, O is the symbol for oxygen. F is the symbol for fluorine. Yep. So instead of just a simple F, what we do is we actually make a little subscript 2. That means that at normal conditions, atmospheric pressure and temperatures, fluorine is going to be a molecule. It's going to be running around with the buddy. Now, the way I remember these 7, because it will make a difference. Long time ago was the German name Hofbernickel. Don't even know if that's a real German name. But if you spell out Hofbernickel, Hofbernickel. Hofbernickel. So with that in mind, I could put little subscript 2s, and I'm reminding myself that though hydrogen's diatomic, oxygen, so is fluorine, so is bromine, so is nitrogen. We have a lot of nitrogen in this room, don't we? So is iodine, so is chlorine. So those are all diatomic elements. This is going to actually be a player. This is not something like, oh, that's nice, and this is nice. The reason this is a player, for instance, if I go to make water, okay, you guys know we use chemical equations to show the formation of water. If I go to make water, it's going to come from hydrogen and oxygen. Over there on the reactant side, on the left, I'm going to have to put H2 and O2. Why? Because they're diatomic elements. Okay, so it is a player in understanding how elements behave. Of course, that's not balanced, just to make sure we're all on the same page. I could probably go ahead and make a 1/2 there, and that would make it balanced. That's a whole nother story. So here are those 7 diatomic elements on the periodic table. We are going to talk about kind of group names. Okay, the video we watched had, like, you guys maybe already know, these are the noble gases, clear over here. They are noble gases, inert gases, rare gases. These are the halogens, beginning with fluorine, chlorine, bromine, iodine, and astatine. So the thing with this is actually all of these, do you see that they are, well, not this one, but these are all diatomic elements. Okay, so we'll kind of, that's how that works. And this image kind of shows you how they're buddying up with another element, or excuse me, buddying up with another atom of the same element. The reason for this buddying up, and we'll talk more about what makes atoms stick together to make a molecule or a compound, and it has to do with the electrons. It's how they like to kind of make it all happen. So Dalton, I don't know, way back when, late 1600s, early 1700s, kind of revisited this concept of an atom. Actually, the concept of an atom had been introduced clear back by Greek philosophers, okay? But he came up and he, based upon his observations and observations of others, I was talking to my mom on the way to work today, and she was like, wow, in astronomy, because I dabble in astronomy and teach intro to astronomy, she's like, they keep coming up with new stuff. And I'm like, yeah, and she's like, well, you think the telescopes are more powerful? Well, they are. But honestly, the beauty of science is that we continue to build on what others have done before us. It's not like we're reinventing the wheel. We're like, hey, dude, that's awesome. Well, let's go ahead and take off on another direction with that information. More observations. So anyway. So Dalton said that all matter is made up of these cute little small things called atoms. Now, in the slide I'm going to show you, which Dalton came up with, the stuff in blue is wrong. So Dalton originally said stuff is made up of atoms. He said these atoms are indivisible and indestructible. That's not true. They're indestructible with ordinary chemical means, but you can switch up your destructive sword, okay, to some sort of nuclear device, and we can split the atom. That's all that's. Okay, another blue thing, meaning that was in his original statement, but it's not true. Dalton said that atoms of the same element are identical in chemical properties. That is totally correct. But he went on to say, for instance, if we pick on copper, he went on to say that all copper atoms have the same mass. And that's not true. We're going to get to today the concept of an isotope. You might have heard of before. And we can have copper, we can have a heavy copper atom, a light copper atom. The thing about, maybe you remember this, the thing about those two copper atoms that have different masses is they have to have the same number of protons, positively charged particles in their nucleus. So he went on to say that atoms of different elements will have different masses and they will differ in their chemical properties. That's right. Dalton said that compounds then are formed when atoms of two or more different elements, different types, join together. And they join together in small whole numbers. So here's the deal there. If you stay in chemistry and go on to, or maybe you've already been in biology, when you look at the formulas for DNA or RNA, they are not small whole numbers. They're whole numbers, yes, but they're large whole numbers. This red now is to just added to his original statement to make his statement correct. So Dalton said, this kind of goes back to the first one. Dalton said that atoms can neither be created nor destroyed, and if you amend what he said by saying during ordinary chemical reactions, then he's correct. Okay, so that's kind of how that works. There's a lot of conservation of fill in the blank. There's the conservation of energy. Energy and matter basically are the two things that make up our universe. But this is kind of three different ways to look at the conservation of matter. Atoms. It's kind of like when we go to the chemistry lab and if we do some sort of chemical reaction, the atoms that you end up with are same as the atoms that you started with. Okay, atoms are not created nor destroyed. If you're doing an ordinary chemical reaction, matter is neither created nor destroyed, and mass is neither created nor destroyed. And we're kind of counting on all of this. Actually, this last one, we're definitely going to make use of that in the chem lab sometimes. You did it with your sucrose solutions. You know, you said by difference then, you can get to the mass of a component of a mixture since mass is conserved. This is kind of a clever little, anybody in here brew their own beer? Are you guys old enough to brew your own? Right. My son-in-law brewed his own beer and he wasn't old enough. But, so anyway, he's okay. He's an electrical engineer. He's fine. So this would be your reactants, like what you start with when you brew beer. Simply, I don't know what sort of thing you ferment, but you have sugar and the thing you want to turn into beer, and then as the reaction takes place, you end up with ethanol, which of course gives you that nice little buzz, and beer, and it does go ahead during the fermentation process to go ahead and carbonate it too. Okay, so, but my point here is, as long as you sealed it before, okay, and I guess there's a science to this, okay, but, and the top didn't blow or anything like that, then you could weigh it back and it would be the same. So that's kind of clever. This one's kind of similar, if you're kind of looking at this lead battery. So this is the new battery on the left, this is the used battery on the right. If you read the captions, it will kind of tell you what compounds you start with and what compounds you end up with when your battery has been spent. And the mass should be the same. Okay, so there's all sorts of interesting, like early on experiments that scientists did, and they kind of came up with like carbon monoxide, CO. Okay, it has a certain mass of carbon to mass of oxygen. Okay, carbon dioxide, CO2. Okay, well, you figure in carbon dioxide you're going to have twice as much oxygen as you had in carbon monoxide with the same amount of carbon. Okay, that's the law of multiple proportions. So that twice as much mass kind of came down to, well, you have twice as many atoms of oxygen for every repeating molecule, carbon monoxide versus carbon dioxide. So this is kind of showing you crystalline lattice structure. Yeah, and showing you different ratios. Okay, so here, just stay awake with me, people. There's 3 subatomic particles that we need to talk about. And you will see them on your Unit 1 exam of sorts, and you'll see some homework questions about them. So I'm going to try to give you a little bit of scale. This is not drawn to scale, by the way. If the nucleus were that big, you couldn't go ahead and make kind of that lighter region to show you where the electrons are. We actually call the electrons are in an electron cloud. At some point in Chem 1, I'm going to kind of switch it up a little bit. The electron cloud isn't always a sphere. Okay, so we'll have to kind of talk a little bit about that. But I already kind of said that in the nucleus we have our protons. We're going to do the symbol P with a plus. And also in the nucleus we have the neutrons. So I'm going to put an N. My superscript here is the 0. So because they're neutral. This cloud right here is my electrons. I'll put an E with a superscript negative. This kind of, there's been experiments early on to find this out, but the electron cloud is basically, I'm going to say, empty. It forms this empty space. And like the slide says, in the nucleus, that's where most of the mass is. Like when I say most, I mean 99.9999% of an atom is in its nucleus. So, in other words, these electrons, and it's going to come up on a slide, they are massless. Massless. You'd be like, oh, Mrs. Snipes, are they really massless? And be like, no. And then, if you're a physicist, you really start to kind of freak out here, because I really think they count the mass of an electron all the time. But we don't in chemistry. So this is trying to give you scale. If the nucleus were the size of a single blueberry, so in the nucleus you have your protons, positively charged protons, neutrally charged, no charge for the neutrons, then the electron cloud would be like the size of a football stadium, which football started, my husband said last night. Watch football. Okay? He warned me. So my point is that there's a lot of empty space in an atom. And I don't know if this is true or not, but I saw this on a documentary that the guy who first figured this out was like, oh my gosh, so you mean we're walking around on the atoms that are making up this floor, and most of the space for that atom is just empty space? And the answer is yes. And then it comes down to, well, why don't we fall through? And then it comes down to, this is how I've heard it explained, the electron cloud around the nuclei of those atoms basically repel the electron cloud of my feet that are in contact. So electron cloud repel each other. So we're kind of like hovering, we're kind of like floating. Anyway, it's kind of neat. All right, this is another, so see, a BB would be smaller than a blueberry. So this is saying if your nucleus was the size of a BB, then the way I read this, then the edge of your cloud would be about 5 stories high, because it'd be like in the center of a 10-story building. Crazy. So let's look at those 3 subatomic particles, the only ones we care about in chemistry. So what do you need to know about protons? They are positively charged. They're found in the nucleus. Protons actually and electrons, remember I said electrons And electrons, well, I didn't say it, but I should use the word repel. Electrons repel each other. Electrons and protons attract each other. So within the same atom, the electron cloud wouldn't stick to the nucleus unless it had something positively charged, and that's the protons. I already kind of said that most of the mass is in the nucleus. So there's only, if the electrons are massless, then what we're going to see actually in the nucleus, the protons and the neutrons weigh about the same thing. Same amount. Protons. Now, this periodic table, I said, said that the number is there's two numbers for each element. The whole number is the atomic number. The atomic number is the number of protons. Okay? Number of protons equals atomic number. Now, if we look at this periodic table or that periodic table, you're going to see, in the video we watched, it skipped through the whole periodic table by increasing. So we have 1 proton, 2 protons, 3 protons, 4 protons, 5 protons, 6, 7, 8, 9, 10, 11, 12. We picked on copper, 29 protons. So I said a minute ago that there are different isotopes of copper, but all isotopes of copper will have 29 protons in them. It defines what copper is. I talked about splitting an atom. Let's see what's kind of an unstable atom. Let's pick on uranium. If we split a uranium atom, it has 92 protons, and I think we have some changing. I don't know. Let's just say we split it in half. Let's see, 45, 46. So we get like 46 protons and 46 protons. Okay? So I know it doesn't work that way, but that'd be like palladium, 2 palladium atoms. And again, it doesn't decay that way, but kind of like that. This is supposed to. Okay. Now on to neutrons. Neutrons, that superscript is 0, showing the charge. What else about neutrons? They are also found in the nucleus. Now the thing about it is I said that the electrons repel each other. Well, so also do the protons repel each other. So if I have uranium and I have 92 protons in the nucleus, they don't like to coexist. So thank goodness what happens is within that nucleus, if that's kind of showing the nucleus, is we have kind of neutrons here to kind of help dilute the influence of them being in such close proximity. So in that sense, the neutrons kind of act as glue. So in a minute, you're going to see a chart with all these 3 subatomic particles and their characteristics. And like I said, you're going to see that the electron is basically massless and that the neutrons and the protons weigh about the same, 1 AMU. Electrons, negatively charged, found outside the nucleus in a cloud, not always a spherical cloud. And so this probably makes sense. We talked about kind of the blueberry versus the stadium, or the BB versus the 10-story building. So when it comes to the volume of an atom, and I think you're going to have some calculations calculating maybe the volume of an atom. The volume of an atom is mostly made up by that electron cloud. I mentioned this a little bit ago. Whenever we have our 7 elements that like to buddy up, like oxygen, it's O2. The reason those 2 oxygen atoms stick together has to do with the electrons. So honestly, for instance, when it comes to, if we're talking about water molecule, H2O, the reason that oxygen stays with the hydrogen, that oxygen stays with the hydrogen, has to do with the electrons that they're, in this case, sharing. So electrons are important in chemical bonds. This kind of goes back to, this just reminds me of Christmas. Now the 2 colors, of course, would represent and I don't know which is which, but the positively charged protons and the neutral neutrons. And then this is the electrons. The reason they kind of show the electrons is not that there are really that many electrons, it's just that we don't really know exactly where the electrons are. And they're very fast and buzzy. this was the table I was telling you about, where over here you can see that each row is a different subatomic particle. We have the protons, the neutrons, and the electrons. You can see where they're located, what their charge is. The last two are talking about mass. And we are gonna, when we talk about how much an atom weighs, we're actually gonna switch gears. And AMU stands for atomic mass units. Okay, AMUs, atomic mass units. And as it works out, I mentioned that the neutrons and the protons weigh about the same. They both weigh about 1 AMU. I guess it looks like to at least 2 sig figs, they're 1 AMU. And see what I mean by massless? Electrons are very light. All right. Atomic number. We've been talking about atomic numbers. I call it the whole number. That's the whole number for each element. Atomic number is kind of counting up as you go across, and then down and across, and down and across. Atomic number, you're going to want to know this. We use the symbol Z for this. And don't ask me why. I need to track it down sometime. My Z's, if you're looking at my answer keys, for whatever reason, have like a little thing through them, just to differentiate my Z from a 2. Okay? So atomic number is the number of protons in the nucleus of an element. Okay? And this goes on to say that with regard to electrons then, and we'll talk a little bit just briefly about things, briefly about things that aren't neutral. But if your atom is neutral, then for every plus you have in your nucleus, every proton you have, then you need to have an electron outside to counteract it, to make it neutral. So for instance, if we pick on uranium, 92, atomic number 92, if it's a neutral uranium atom, then it has to have 92 electrons outside to kind of counteract the 92 protons it has. That's one of your little game that you're going to do with your homework to count subatomic particles. So this kind of drives me nuts. To me, an A, and I'll try to say this quietly so I don't confuse everybody. To me, an A should have been atomic number. It's not. The Z is the atomic number, and the A is the mass number. Now, mass number and mass are not the same. Okay, mass number and mass are not the same. Mass number is counted, so this is counted. It probably already says counted. But mass number, A, is equal to number of protons plus number of neutrons. Mass number, not so surprising. You're focusing on the 2 subatomic particles that give you mass. And it's not the electrons. Okay. So atomic, since it's the protons that give the identity to an element. You know, pick on silver. Where is it? Ag. There's silver. Okay, every silver atom is going to have 47 protons. 47 is its atomic number. Okay, so if you tell me I have an atom with atomic number 47, I'm like, oh, that's silver. Okay, so it defines it's the number of protons, and the number of protons define what element the atom is. Okay, atoms of different elements will have different atomic numbers. Make sense? Now this goes back to kind of what we picked on Dalton for, because it's not true that if you have a mass number, how do I say this? Mass number is not unique. Atoms of the same element can have different mass numbers. An example, I'll go ahead and keep picking on copper, although a lot of them have different, what we call isotopes. It's quite possible to have 2 versions of copper. They both have 29 protons, but they have different number of neutrons. Okay. Now, if they have different number of neutrons, guess what? They're going to have a different mass number. It's possible, and I don't know where those occasions where the elements are relatively close to each other, it's possible to have atoms of different elements that have the same mass number. I kind of call neutrons like the little spice, the little salt and pepper that nature throws in. Now, granted, it's not that easy because there are different versions of an atom that will be stable or not stable depending upon the ratio of their neutrons to the rest of the subatomic particles. So all this talk about isotopes. Isotopes have been what I've been talking about. If you have an atom that has the same number of protons but different number of neutrons, they will have different masses. So it's all about the neutrons. If they have different neutrons, then they have different mass numbers. So remember the symbol for mass number is A. That's the number of protons, which is set in stone, plus the number of neutrons, which will vary, can vary. Now, not all elements have multiple versions. These actually, and it's kind of like an oxymoronic term if you ask me, these listed here, these 6, for example, have only one isotopic form. Like, isotopes by definition mean, I don't know. But they will only have a set number of neutrons in nature. It's not to say that we can't, outside of nature, go ahead and try to shove a few more neutrons or take a few neutrons out. These have 2 isotopic forms, and these have multiple isotopic forms. Obviously, this isn't anything you necessarily need to commit to memory. You don't commit to memory, please. But this book is dun, 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 all online now. But before the internet, it was quite a handy tool. And I try to say that this is like for people who have too much time on their hands. They come up with all these different properties of elements and compounds. So one of these tabs, and I got too close to my candle one time, one of these tabs actually, table of isotopes. Wow, it's a big section. So it will list, yeah, the pink, it can't hurt, it smells pretty kind of good actually. You can kind of see how it's grouped. It's a little small writing. But it tells you, for instance, if we pick on this one right here, magnesium, goodness gracious. So I got right here, those are the different isotopes of magnesium. And we're going to talk more about this next week, but they have to tell you how abundant it is and how much each isotopic form weighs. But, all right. So there are cool things that you can do with isotopes, especially like in imaging, like medical imaging. You can have one particular isotopic form. If you've ever had like I think this is right, the barium thing where you drink the drink and it kind of goes where it's supposed to go and then they image you. Okay, so they are tracking a particular isotopic form, okay, of the thing. So we need to be able to differentiate isotopes. Carbon dating. I don't know if you've heard of that, has nothing to do with like dating, but carbon dating uses something that was once alive to go ahead and see how much isotopic form of carbon-14, I believe, they still have remaining. Carbon-14 is kind of more of an elusive version of carbon. So a more common form of carbon is this carbon-12. When they say carbon-12, what they mean is that 12 is the mass number. Let's find carbon on the periodic table. Okay, so a carbon atom we know has 6 protons, every carbon atom. Carbon-12 has a mass number of 12. Well, let's see, of that 12, 6 of those are from protons. So 6 from neutrons. So that's how that carbon atom rolls. If it's neutral, we have 6 electrons, 6 protons, and 6 neutrons. So these are all ways to show that particular isotopic form of carbon. This one down here is probably my favorite down here because it goes ahead and it gives the symbol. It hits you over the head with anything you can pick up from the periodic table. It's atomic number, and this is the mass number. And this is always the format. So it's always on the left side. The upper one is the mass number, the lower one is the atomic number. So this is kind of the format. So you'll have some homework to kind of get you ready to. Is there any element X? Some of the names of the elements are interesting. Did you hear that? Especially the newer ones, the ones I don't have up here. We'll have to update this. I might get little squares.
Yeah, I like how that one's
Right. The UU actually designation means they have successfully isolated it long enough to count it as an element, but they haven't named it yet. And if you read about it, sometimes things will be will make the periodic table or tentatively the periodic table and they'll be withdrawn. Okay, and it's very they're very unstable. So here we have the Christmas tree thing going on again. Boron, so if I look at the periodic table, we must be looking at what? 5 protons. So whichever one of these has 5, looks like the red ones. To me, I've got 5 red ones there, 5 red ones here. So that must be my protons. Note what's changing are my neutrons, my green ones. I have 5 over here and I have 6 over here. So here on the left then, 5 plus 5 is 10. That's number 10, this is boron 10. 5 plus 6 is 11, so this is boron 11. So this is the sort of thing you might be faced with. So what do you think? Do you guys have the answers here? So how many protons does this have? 9. 9 protons. How many electrons? 9. Very good. How many neutrons?
9.
How'd you get 10? It is 10, but yeah, 19 minus 9. Okay, cool. Well, yeah, very good. So 9 protons, 9 electrons, and 10 neutrons. You got it. One of the things about science is they're all about like trying to be as concise as possible. So I mean, I can really appreciate this up here. That's the opposite of literature. It seems like sometimes I am not a writer. I appreciate good writing, but so I'm like, yeah, that's fluorine, mass number 19. To me, the atomic number, the 9, is kind of a little bit redundant because if you had a periodic table handy, you could be like, oh, I know it has 9 protons because it's fluorine. Oh, by the way, there are some great apps for your phone, free apps, just periodic table. Go out and look at them. I think I paid like $5 to get a deluxe one, but it's worth it. All right, we'll be talking more about this, but I mentioned a little bit ago that if something's neutral, like a uranium atom, since it has 92 protons, if it's neutral, it has to have 92 electrons. Well, if something's not neutral, we call it an ion. So you have 2 options for ions. If we stick with uranium, which I'm not sure that's necessarily a good example, if we stick with uranium, it's possible to actually it's possible to actually take some of those 92 electrons and for those 92 electrons to split. I shouldn't have said that because split uranium, to leave. And again, I'm probably kind of butchering this with uranium, but if you were to kind of show the flow of it, you could take something with a nucleus like that has 92 protons and it has 92 electrons, and let's just say it loses 2 electrons. Now we still have 92 protons and we only have 90 electrons. Okay, so this is uranium. So in this case, do you see where, if I were to say, do you think it's positively charged or negatively charged? It's positively charged. Yep. Specifically, it's positively charged with a +2, just because it has 2 extra protons. You know, this took me a while as I was teaching it early on, but you guys, does this make sense? Protons will never come and go. Electrons, yeah, will come and go for various reasons. All right. Well, let's try to pick one that does do it. So we call this a cation. And if you kind of look at T, it looks like plus, not to be confused with a cation. Okay. The other option And we'll pick on sulfur. How many protons in a sulfur atom?
16.
Yep, 16 protons. And if it's neutral, how many electrons? Yep, 16 electrons. In this case, I'm going to actually, and it does this, pick up 2 electrons. And it has the same nucleus, 16. And now it has 18 electrons. So is it positively charged or negatively charged? It is negatively charged. Specifically, it's a -2. And we call this an anion. Okay, so now I kind of want to introduce that real quick or briefly because I want to be able to look at kind of the shorthand notation and knock out the electrons too. So here we go. You kind of saw me do this with the uranium and the sulfur. What I did in the upper right-hand corner, if it lost electrons, I put the cation, that's lost something. If it gained electrons, I put it was negatively charged and how negatively charged it was. So let's look at an example of how that would work. We could pick on calcium. Since it's positively charged, did it lose or gain electrons?
Lost.
Let's see, it's positively charged. It lost electrons. Yes, very good. Because it has too many protons in it. So how many protons does it have? 20. Thank you. It has 20 because they're embedded in the nucleus. How many electrons does it have?
18.
Does everybody buy that? It's 20 minus 2, or 18. How many neutrons does it have?
19.
19. Yep. So the 20 came from the number of electrons it would have if it was neutral minus its charge. And the 19 came from its mass number, 39, minus the number of protons, which was 20. It's like a little puzzle. I think I have one more. That was a cation. This is an anion. So since it's negatively charged, did it lose electrons or gain electrons? Gain. And it's a -1. See, if there's nothing over there, it's implied a -1. Sometimes I would put a -1. Okay, so how many protons does it have? 17. How many electrons? 18. And you get 18 from taking the number of protons it would have if it was neutral. Sorry, the number of electrons, it would have if it was neutral. 17 electrons, and to that you add 1 electron because of the charge. How many neutrons? I use a calculator sometimes. I'm like a 19. 19 is your mass number, 36, which is your protons, plus neutrons, minus your protons, which was 17. Yeah, feel free to use a calculator for those. Okay. Any questions? Well, the other slides are just kind of like little stuff I just didn't go to. It talks about Coulomb's law, which would be the attraction or the repulsion of light particles and the attraction of unlike particles. So I just kind of blew that off because I can. And then we get to, you didn't think I could do it, did you? Then we get to the assignment slide. So this will be due on Monday. We have a long weekend Monday. Oh, we're into the dirges of fall semester. Very good. Have a good weekend, guys.
You too.
Thanks.